So remember, the idea here is that we're looking at area under a curve.
Yeah.
So the curve, if it's curvy, like this one that we finished with, doesn't have an area formula that we know of that we can find the shape. And it is curved, which means if you zoomed way in at the curve and you were looking at boxes on a coordinate grid, like you were actually looking at counting squares, which is what area is, you would have a bunch of little tiny partial squares. So when we look at finding the area, the formula itself doesn't exist. But we can estimate areas of things using shapes we know. So if we were looking at a triangle, for example, the way we develop that formula is because we look at partial rectangles. We look at if it was a rectangle, here's its formula, now we can cut it in half because we know that there would be two triangles in every rectangle. But what you probably did before that was you actually looked at on a grid, how many squares was I filling up, since that's what area is. And so when we think about trying to find this area, we can use familiar shapes. So you guys knew yesterday the formula for a triangle. What was it? Okay, and you knew the formula for rectangle. Okay, we can use formulas like those to estimate this. So let's imagine this guy here. Again, it's on this grid. We're trying to find its area. And since it is y equals x squared, let's say that we had a decision of how far we wanted to go, because we know the area is going to change based on how far over we go. We want it from 0 to 2. So this is actually 2. And we've got this area that we're trying to find. We can estimate it using those familiar shapes that we already know. So let's think about a rectangle, for example. If I were to take that space right there and cut it into two rectangles, one way I could do it would be to cut it right here at the line x equals 1. And then I could draw rectangles where the right-hand edge of the rectangle was on the curve. And if I stayed consistent with that and I drew another rectangle over here, it would be really simple for us to find the area of both of those rectangles. So I could find the area of the two rectangles, add them together. How would that total area that I find when I do the whole rectangle that I draw, and I add these two together, how would that compare to the actual right answer, even though we don't know what the right answer is? If we went
double it, almost about.
Visually speaking, it looks kind of like it, doesn't it? Definitely bigger, though. We don't know. Even if it's not double, it might, for all we know, it could be triple if I didn't draw this well to scale. We don't know. It could be less than a double, but it's definitely bigger. How do you see the bigger? How do you know that it's bigger? Yeah. Yeah. And so we're finding stuff that's not shaded, so we know we're going a little bit over. There's quite a bit. Zach's saying it looks almost double to him. If I wanted to have less extra, if I wanted to be closer to the correct approximation, I could take this same idea here, same curve, going to 2, and let's think about what would happen if we were to make more rectangles. So if instead of 2 rectangles, I cut this into 4 chunks, and I made a rectangle that went up to the right-hand edge of the curve, and I found its area. Again, to the right-hand edge of the curve and found its area. Right-hand edge of the curve, found its area. Right-hand edge of the curve. And I found those blue rectangles right there. And what I wanted was the black part that I'm coloring in. I still have extra. You still see white space. Do you agree that it appears like it's less white space? So back in the old days, if we imagine ourselves being a Greek mathematician, trying to do this work, trying to find the estimate for the area under the curve, because that's where we put ourselves when we're in calculus class. A lot of times we think through, how does the math come to be what it is? They didn't have formulas for this, but they did have the ability to find the area of a rectangle. So what they realized is, if I were to actually now take those 4 rectangles and do 8 instead of 4, I'd have even less white space. And as I kept going, I'd have less and less white space the more rectangles I have. And so the question is, how many rectangles should I have to be reasonably sure that I'm pretty close to the right answer? Ideally, I do. I want infinite rectangles. How do you draw infinite rectangles?
You do a rectangle and you put it in the
There's not really, well, there is kind of a formula for that, Victor, you're right. Well, they're called limits.
Oh boy.
We talk about limits from this idea of as something approaches infinity. Those were the very first limits we had. So if we're looking for an area between two spaces and we're talking about drawing these rectangles, your idea is, and the idea of the Greeks, you think just like a Greek mathematician, was let's imagine we could do it with infinite rectangles. So I said this curve. One thing I want to point out is in both of those pictures I drew, I started at 0, 0. We're going to actually find areas between any two x values we want. So this is between A and B. A isn't necessarily at 0, 0. It's just someplace along the curve. But we're going to use this idea of infinite rectangles between them. And there are different ways to do this. In calculus, we'll look at drawing different kinds of rectangles. But we're going to, for right now, stick with one way of drawing rectangles, which is picking places along the curve to have be the right-hand edge of a rectangle. And so we're going to draw these rectangles coming down where all of their right-hand edges will always form sides of rectangles. Every single time we're going to know that we will be a little bit over if we were to do this. Can you think of ways that you could position your rectangles differently where you wouldn't be a little bit over?
Well, we've done this before. But I said the left hand corner of the rectangle is the inside.
If you did that, yeah, if you were to do that and draw it on the left-hand side and draw little rectangles, you would just be a little bit below it. And so you'd be a little bit under in your estimate. And we'll explore that option too. You could also position your rectangle where the middle of your rectangle was actually on the curve. So you don't have to draw this on your paper, but just so you can see kind of the difference, if I were to put that as the top of the rectangle right in the middle, I'd have a little white space and a little bit of blank space. So this one you can see it a little bit better. I'm missing this piece, but I have this as extra. So that's another way to think about the rectangles. There's lots of ways that you can approximate this area, and then there's some ways that you can actually find the area. We're going to start with thinking about this as an approximation with it underneath the curve this way. So I want you to think about the area under this curve using these rectangles here. We've got values that we're going to be looking at to find the actual areas of the rectangles. We're going to have to add them all together. So the width of each rectangle, one important thing, or the change in x that we go from side to side, since the first rectangle here that I'd be looking at would be from wherever A starts, we're going to call this place where I would hit the first time, the first side of my rectangle, I'm going to call it x sub 1, meaning it's the first x value that I'm going to look at. And then I'm going to have to know where the second x value is. I'm going to have to know where this third x value is in order for me to start thinking about finding the widths of these rectangles. We're going to divide them so that each of those delta x's, or the change from side to side, is the same amount. So delta x just stands for literally how wide is your rectangle. You need width of your rectangle for the area. What's the other thing we need to find the area? Okay. So we're going to need to take the heights of the rectangles, and if we multiply them together, we can find the area of the rectangle. Now, depending on how many rectangles we do, we're going to have to add up 2 of these, 3 of these, or 4 of these, or an infinite of these, as Megan said. So you said to find the total area, you're going to have to add up the sum of all your rectangles. And all I have to do is multiply their bases and their heights together. So their bases would be your delta x every time. How would you find the height of your rectangle though? If you know that this is like y equals x squared, for example.
So, if it's on the right side, you can just plug it in.
So if I was here and x was 2, for example, and I wanted to know where this was, he's saying 2 could be plugged into x squared, and you would know that you were 4 high. And that would be the side of that rectangle. But everyone agrees that this rectangle is taller. So the question would be, what number x was I at? If that was 3, and I plugged it in, how high would I be? Yeah. And if this was 4, I would be 16 high. And so I would keep having to plug them into the function. So I'd have to plug in whatever that first x value was. We call it f of x sub 1, meaning I'm going to plug in the x value into the function, and I have to multiply it by how wide that rectangle is, which is delta x. And then I'd have to add up the second one plugged in times its width. And I'd have to add on the next one times its width. And I'd have to keep doing this over and over and over again until I get to the last one. We're going to call the last one x sub n, meaning the nth rectangle, since n stands for the number of rectangles that I want to do. We could write this whole thing a lot nicer if we wrote it as a sum. So that notation that we used to use when we talk about a sum. If we say sum, you'll notice that every time you have a delta x in it, and you also have f of something, the number starts at 1, 2, 3, 4, 5, all the way up to n. So we would say, I want f of x sub I, where I starts at 1. And then it becomes a 2, and then a 3, and then a 4, all the way until it becomes an n. I'm going to use I. Technically, I could use anything, but we're going to keep going with this I, so it might get confusing if you don't. And they get multiplied by delta x every time. Does that formula there, or at least the setup of the formula, look familiar? When have we used that before? Yeah, when we were doing all those patterns,
Yeah.
we had that sum notation, so we have to remember how to use it. But remember, it actually means take the number on the bottom, plug it in, plug in every integer until you get to the number on the top, and then you stop. And you add all your answers together. That's why we have that big sigma saying add them all together, and you'll have your final answer. Now, if this is our formula, you're going to have to be able to figure out, this part will be easy. You have an equation, you're going to plug in numbers. This part right here, where does it come from? How are you going to know how wide each rectangle is?
So how many rectangles are there going to be under this curve?
N.
Well, then you take how long your segment is from A to B and you divide it by it.
So if I wanted 3 rectangles, I'd figure out how wide it was from here to here, and I would divide that into 3 equal chunks. On my picture I drew on this page, over here, that would mean I wanted 2 rectangles. I went from 0 to 2, so how wide was each of your rectangles? But over here, I went from 0 to 2, and I cut it into 4 rectangles. How wide was each of them? A half. So all I need to know is how long is this, and how many rectangles do I have, and then I'm going to be able to find it. So I can take, to find this, how long is my segment, how far is it from B to A, and then how many rectangles do I want? And that's going to solve for that part. Now we want how many rectangles?
Infinite.
And so the question is, if we want infinite rectangles, how do we do this area formula as n approaches infinity? It's with a limit, and we already know how to evaluate limits. So the good news is, we know how to do this, but we're gonna have to set up a limit. And the setup, like you were doing the other day with the definition of derivative, the setup is the tricky part. Once you get it all set up, it's a matter of evaluating limits the same way you guys have been evaluating limits. We're gonna have to struggle through today how to get them set up. But I'm gonna plug in this limit, as n approaches infinity, is literally being taken of the sum of, from I is 1 to n, of this function. And it's this crazy looking notation. Very, very advanced math notation. This right here, you're gonna see written out in your calculus book. And it's the same notation every time you go to find this, every time you go to estimate this area. And so, as mathematicians, we try to make it a little shorter to summarize what we're doing. And they call it an integral. And they use a symbol to represent most of this to make it look a lot easier. All of this stuff at the beginning, they'll denote with this long, elongated S. You might have seen that before in math books. Probably not in any of the books we've been working through. Has anyone seen that before? Like on some of your higher level questions? Those, you guys don't get to take out stuff, but I bet people have run into that. That right there is called an integral symbol. And you're going, remember, between A and B. So they tell you where you're going between. And then they say, this is the function you're doing it for. And because we now work in Roman letters and not Greek, they use a dx instead of a delta x. But all of that, it looks a lot nicer and cleaner. It means everything that's up above it. So this is actually called a definite integral. And there are ways that you can evaluate this definite integral. And we're going to study some of them. We're going to do them using limits because we know how to do limits already. So it's one less thing we have to learn. In calculus, you'll actually look at other ways that you can evaluate it too, but we're going to use the skills we've got. So we're going to actually evaluate the limit. We're going to look at how to set up the limit today, and then you're going to get to take a look at actually evaluating it to find the answer. But in your book, you're going to see the notation on the bottom because it's shorter and nicer and cleaner looking. We're going to use what we know it actually equals so that we can set up a limit. Okay? Sounds like a lot of fun, huh?
I'm having a blast.
I know. So, we're finding the area under a curve. So if it's called a definite integral, that process is called integration. And we're going to stick with right now this area that we already started thinking about. We're going to find the area under this curve, x squared. And we're going to find it from 0 to 2. And we're going to try to do it with infinite rectangles so that we don't have so much white space. Just for fun, let's think about if we did do it with like 2 rectangles or 4 rectangles before we do it, just for fun. Okay. I'll give you a second to finish getting this copied down. So just for fun, before we do this, because I think you guys need to do some thinking and some moving around a little bit,
Bless you.
what I want you to do before we actually start is I want you to just look up here. You don't need to write this in your notes. I want you to, based on what we just said about how to find the heights of these rectangles, I want you to talk with your neighbors, first of all, about how to find the area and actually do it. Find me the area that you'd estimate using 2 rectangles over there. And then I want you to find me the area using 4 rectangles. I want you to decide as a group what you think the answer is and make sure everybody understands how to do it, because I am going to ask you in a minute to move around and talk to somebody else about it. It's not at your group. So take 4 minutes to make sure everybody at your group agrees on how big the area is using these 2 rectangles, and then using those 4 rectangles, assuming that it is y equals x squared each time. See what you can come up with. You can do it in your notes or just on some scratch paper. Tell your partner or partners the area when there are 2 rectangles. Count of three. On count of three. 1, 2, 3, go.
5.
Did you say the same number? Okay. Now I want you to stare deep in their eyes. This is the scary one. When I say go, I want you to tell them the area based on 4 rectangles.
Alright.
1, 2, 3, go.
3.5.
If you said the same number, oh man, I hope we're both right.
I think we put
And if you said different numbers, talk about how you got those numbers real quickly.
I don't remember. I didn't write anything.
Oh, it's
Okay, it's tricky math. You guys go back to your seats.
I don't want it.
okay.
Some people have answers that they agree on, some people they have answers that they don't. If I were to expand this and say 6 rectangles, or 8 rectangles, or 10 rectangles, the tricky part is that you have a lot more room for mistakes, more decimals in your answers. You get closer to the right answer, but it'd be tricky. So, that is why a limit, if evaluated correctly, is going to be so much better than trying to do this. Now, I did hear at least a couple groups agreeing on an answer. You could probably redo the process if I gave you more rectangles, but it's tricky. So, enter this idea of a limit. We're going to take this problem here, and we're going to set it up with an integral, first of all. This is the way you'd see it in a book. It would say the integral from 0 to 2 of this function that we're working with, which happens to be x squared, dx. This is the way it would be set up in your book as a, here's the problem I want you to do. We're supposed to take this problem and evaluate a limit. As n approaches infinity of this sum that we're working with, starting at 1 and going until we reach n. You had in your definition of this limit, the next thing said f of x sub I, meaning the function with x sub I plugged into it. The function is x squared. So if I plug x sub I in, it would read x sub I squared, and then it said delta x. So this limit isn't tricky once we get it set up as a limit, and right now it's set up as a sum. Sum means we add a bunch of things in progression up over and over and over again. So I want you to think about this thing. Now this piece here is the weird looking piece, but remember that is x sub I plugged into my function. That's all I did. And you're going to have to do that every single time you set one of these up. You're going to have to plug the x sub I in for x in the function. It just so happens this was x squared. So step 1 is we got to figure out what these pieces actually are. Because this piece looks weird, and this piece looks weird. Delta x. You guys told me a minute ago that you could find the width of your rectangles, essentially, by taking how long is the segment divided by how many rectangles are you doing. In this case, you're going from 0 to 2. So how long is that segment? From 0 to 2. It's 2 units. I do 2 minus 0 over n, or in other words, 2 over n. What about x sub I? X sub I is talking about the right-hand side of your rectangle. That's the number that we're trying to plug into the function. How do you figure out that number every time? When you guys were just doing those areas with your rectangles in your groups, how did you figure out what number you were going to plug in to the thing and square for your rectangle? What's that?
The base.
The base. The first time you plugged in 1. The second time you plugged in 2 on the 2 rectangles. But when you'd have the 4 rectangles, you guys had to plug in a half. Then you had to plug in 1, then you had to plug in 1.5, then you had to plug in 4. How did you figure out what numbers you were plugging in? How did you know where your first one was?
So we took the change in x that we had. half. So we went with the rectangle,
like a half, for example.
and we just added it from our starting point. Right.
So how many of those halves over were you? So at the end of the first rectangle, you're only a half over, but at the end of the second rectangle, you're 2 halves over. And then at the end of the third rectangle, you're 3 halves over, or 1.5. So if we take that in terms of our math, you're telling me I'd start at the beginning, which is A, and I'd add on how many delta x's have I moved? I start in this problem at 0, and I add on a certain number of delta x's. I delta x's, well, delta x is equal to 2 over n. So I'm going to simplify this. I times 2 over n is 2i over n. So I have these pieces here that I can plug into my formula. It says the limit as n approaches infinity of the sum from 1 to n of x sub I. Well, x sub I is 2i over n. It says squared up here times delta x, which is 2 over n. And this is what we have to take the limit of. This is going to take practice. I'm not saying you necessarily do this on your own, but are there questions about how I just plugged in, how I changed from the thing I had in black before to this thing in black? Look at just what I changed. Do you see where I changed it from? Any questions on what goes in where? Okay. Let's simplify it because it looks really nasty. What do you see in here that could get a little simpler?
Nothing. It's complicated.
Well, it is complicated, so let's make it simpler. Unless it's already simple, let's make it simpler. You have 2i over n being squared multiplied by 2 over n.
A squared equals 4, is 2 over 8i squared over n cubed.
Where did he get that? 2i squared. Somebody repeat what he just said. What is 2i squared? 4 what? 4i squared, and then multiply that by 2? Okay, that's what he said. So he has 8i squared on top. This 2 over n. So we were bringing it all together as one nice little piece. And then on the bottom it says n squared already times n. So I heard him correct himself and say n cubed on the bottom. That's what he's taking the limit of. So what we're going to do with this is actually plug in numbers. That's what sum means. Sum means you have to plug in 1, and then you have to plug in 2, and then you have to plug in 3, and then you have to plug in 4. I want us just to look for a pattern here. That's the last job for us today. If we were to evaluate this actual sum, you would take all of this stuff and you would plug in 1 for I, and then you'd plug in 2 for I, and then you'd plug in 3 for I, and you'd keep going. What do you see in here happening over and over and over and over again? You're going to keep going until you plug in n. What pieces happen every single time? So the n cubed part on the bottom? Yep. What else happens all the time? He says he sees an n cubed every time. What else does he see every single time?
8.
So really, this is like 1 squared plus 2 squared plus 3 squared all the way down with that up front. And that's the limit we're going to evaluate. We'll stop there for now.